Welcome to this first lesson in this series on classical mechanics. In this video, we're going to be looking at the principle of least action. Now, this is going to work quite differently from normal lectures. So accompanying this video is a booklet that you can fill in and complete. And this booklet will firstly help you take notes as we go through the video, but will also contain questions and activities for you to complete, which will really help you get the most out of this video lesson. Why do we care about Lagrangians and Hamiltonians? Well, firstly, they make some difficult mechanics problems much easier. And this is because they're just about energy, so you don't need to worry about vectors like you do in normal Newtonian mechanics. But I think more importantly, for people who want to go on to do more advanced theoretical physics, and that is Lagrangians and Hamiltonians are the language used in quantum mechanics and quantum field theory. And the main reason for this, or a main reason for this, is about symmetries. So Lagrangians and Hamiltonians make symmetries very obvious. And this is important because all of the standard model is based around symmetry. So before we can do any calculations, we're going to need to introduce some notation and just some key ideas. And all of these are written out in your booklet, so you can just follow along and just write maybe some key explanations or some key definitions. So we have a particle that's travelling along that trajectory drawn in the top left. We're going to call the position of the particle q, and it's a function of time, because obviously the particle moves. And the reason we've used the quantity q is that these are generalized coordinates. And by generalized, I mean it doesn't have to be the normal x, y, z Cartesian coordinates. It could be polar coordinates, could be cylindrical coordinates, it could be coordinates you've never seen of, and will only be useful for a very particular problem. The point is, the coordinates could really be any coordinate system. And as well as the particle's position, we also have the particle's velocity, where the dot here is the time derivative. And again, this is a generalized velocity, and it's generalized because it's not necessarily normal velocity. It could be angular velocity or something completely different entirely. It's just the time derivative of position. And the particle is going to start at q of t1, so here's the start, and it's going to finish at q of t2, so here's where the particle ends. Now, the key quantity here is the Lagrangian, and this is just a function of position and velocity, and maybe time, but to be honest, quite rarely. And you haven't seen the rules on how to construct the Lagrangian yet, or really what it is. So for any examples we look at today, I'll give you the Lagrangian, but what's important is it's just a function of position and velocity. We'll look at more specifics later on, and we'll look at how to construct it in later videos. And then finally, we have the action. And to calculate the action, we integrate the Lagrangian along that path. So the Lagrangian is just a function, and we just integrate it between the start and the end. But to be honest, I've never actually integrated the Lagrangian to calculate the action. It's only ever just used as a tool to derive some equations later on. The key principle that underpins everything we're going to see in this course is Hamilton's principle. And this says that the path a particle actually takes when travelling from its start point to its end point is the path that makes the action stationary. Now, this is sometimes called the principle of least action, but it's not necessarily that the action is a minimum. So if here's our physical path from its start point to its end point, we're going to call the coordinates of the particle along this path q of t. And the action, as we calculate by integrating the Lagrangian along this path, we're just going to call s, as we did before. Now, if we consider a slightly different path, so a path that's close to the real path, but maybe slightly deviated from it in some way, we can call the coordinates of this q plus delta q, where delta q almost tells us the difference between the two parts. Well, this has a different action if we integrate the Lagrangian along this path, and we're going to call that different action s plus delta s, where delta s is a small deviation between the action of the real path and this slightly perturbed path. And if the action is stationary, then this deviation, this difference, delta s, should be 0. That is, these two actions should be equal. We have just said that the difference between the two actions, so that was delta s, must be 0 because the action is at a stationary point. And we can show that, to obey this condition, the path the particle must take obeys this equation here, which is called the Euler Lagrange equation. And this is essentially the equivalent of Newton's second law. It's our equation of motion. And a couple of things to notice is that these here are partial derivatives. However, this d by dt out the front is a total derivative, and so often when we're calculating this total derivative, we will need to use the chain rule in some way. Now, this derivation is in your booklet, or at the very least, the algebraic steps are in your booklet. I would pause the video here, read through the derivation, and annotate each line. If you can't do it, or there's a few steps you're stuck on, we'll go through them all on the next slide. Alternatively, there's some suggested reading in the booklet, which you can go to and it will explain the derivation. Hopefully now you've had a chance to go through your booklet and start to make sense of the derivation. If there are a few steps that are still confusing, that's okay. I'll go through them now and you can follow along with your booklet and annotate each line as we go. So the first line is just the fact that the action is stationary. So the difference in the action of the true path and a slightly perturbed path is 0. Then to get to the second line, we've done two things. Firstly, we've said that the difference in the action is the action of the slightly perturbed path, which was s plus delta s. Take away the action of the real physical path, which is just s. And then we've said that the action is the integral of the Lagrangian. To get to the third line, we have used the chain rule, which I've put up on the screen there for a function of two variables. Except it's not of two variables, it's of both position and velocity, and in fact there's potentially several positions and several velocities. Hence there is that sum out the front. To get to the fourth line, all we've done is expand the brackets and pull the sum out the front. To get to the fifth line, what we've done is integrate that last term in the fourth line by parts. And I've put the by parts formula up on the screen. Except here, because we're integrating with respect to t, the prime is the same as the dot. Now, why this is important is that now the first two terms both have a delta q. Then they don't have a delta q dot, and we'll see why that's important in a minute. Then to get to the next line, we notice that the thing in brackets on the right, so that fully evaluated term, is 0. And now why is this 0? Well, that's because the path had a fixed start and end point. And so delta q of t1 and delta q of t2 are 0. You can look back at the diagram to see that the perturbed path starts and ends in the same place as the real path. Then finally, to get to the last line, we've just compressed everything into one bracket. And this is why we wanted both terms to just have a delta q. It means we've been able to pull that delta q out of the brackets. And now, in order to set this to 0, we need the thing in square brackets to be 0. We can't have the whole integral 0, or rather, the only way to always make the whole integral 0 is to have those square brackets equaling 0. And the reason for that is delta q is arbitrary. It could be any path. And so we can't rely on that being 0, or for the whole integral being 0 in some way there, things cancel. The only way to ensure it's 0 is to have the thing in square brackets be 0, and that's exactly what the Euler Lagrange equation tells us. We're now going to see some examples where we actually calculate the motion or the equation of motion for the paths of different particles. I am just going to give you the Lagrangians, but they are all real Lagrangians that could come up in mechanics problems. And all these equations are in your booklet, so you can follow on with the working as I put it on the screen, and then you can pause the video and have a go, and then I'll put the answers up. So you definitely don't need to write down the question, you can just think about and focus on the solution. So if here's our Lagrangian, we need to work out the equation of motion. So our coordinate here is x and the velocity is x dot. So we're going to use the Euler Lagrange equation, except instead of q, I've just replaced it with an x. So firstly, I'm going to do the dl by dx part of this. So we differentiate the whole thing by x. However, that first term doesn't depend on x. It depends on x dot, which is a different variable to x. So that goes to 0. And then we differentiate that second term and simplify, and we have minus kx. Then we're going to calculate dl by dx dot. Similarly, only the first term contributes because the second term is not a function of x dot, it's just a function of x. And now we need to do the time derivative of that dl by dx dot term. So we take the time derivative of mx dot, which becomes mx double dot. So we've gone from the first derivative of x to the second derivative of x. And then finally, to get the equation of motion, we put all of this together, being careful of signs. Notice there's a minus sign, or it's a 2 minus signs, so in the final answer, kx is positive. Or we can rewrite this, something that looks a bit more like Newton's second law, with mx double dot equals minus kx. And this looks like, and indeed this is the Lagrangian for a mass attached to a spring. For the next question, I would say pause the video, work through it in your booklet, and then I'll kind of just throw the answers onto the screen and you can check your work, make sure you've done the right thing, make sure you understand what's going on. Okay, so now you've had a go at this and we've tried to find the equation of motion yourself. Here is the solution. And in fact, this is the Lagrangian for a particle in a gravitational field or in an electric field or something like that. Finding the equation of motion for this Lagrangian is going to be a bit more complicated since we've got two coordinates here to worry about, r and theta. So I'll go through this one step by step to show you how I would do it for two different coordinates. So because there's two coordinates, we're going to have two Euler Lagrange equations, one for r and one for theta. So I'll do the r1 first. So to calculate dl by dr, we see that there's two terms that contribute, two terms that have an r in it. So the first term and the third term of the Lagrangian. And we differentiate these and we get mr theta dot squared minus kr. Next, we're going to calculate dl by dr dot, and that's just mr dot. Then we're going to do the time derivative of this, and we get mr double dot. And we put all of that together, and we have mr double dot squared minus mr theta dot squared plus kr equals 0. And I'm not going to rearrange it into a different form. Now we need to calculate the theta equation of motion. So I'm going to start with dl by d theta, and there's no thetas in the Lagrangian, there's just a theta dot. And so this derivative is 0. Then I'm going to calculate the L by d theta dot, and only the first term contributes. So we have mr squared theta dot. Now we need to do the time derivative of this, the time derivative of mr squared theta dot. And this is going to get complicated because this time derivative is acting on both an r and a theta dot. This is when we're going to need the chain rule. So, differentiating the first term, or the first quantity in there, the r squared, we differentiate by r, and then we differentiate r by time. So hence there's that extra r dot at the end. And then for the next term, we differentiate the theta dot. So we have mr squared theta double dot. And we put all of this into the Euler Lagrange equation, and this is what we get. Mr squared theta double dot plus 2mr theta dot r dot equals 0. And for those of you who have done Newtonian mechanics in different coordinate systems, you might recognize this as the acceleration in different coordinate systems, or really more specifically, in a polar coordinate system. For the final question of this lesson, have a go and calculate the equation of motion for this on your own, except here notice that the L is similar to the R before, but now L is just a constant, it's not a coordinate. So pause the video and have a go. So now you've had a go, I'll put the answers on the screen. So here's the answer for the Z equation of motion, and here's the answer for the theta equation of motion. So, in summary, we introduced the Lagrangian, which was for now just a function of position and velocity, and we introduced the action, which is the integral of the Lagrangian along a particle's path. And we've said that for the real physical path, the action is stationary. So if the path deviates slightly, the difference in the action is 0. And that leads us to the Euler Lagrange equations. And these are essentially Newton's second law, our equation of motion for our system.